All right, I feel complete. I've got my list of rules for trig proofs here. Nothing's going to stop me now. Let's do some trig proofs. So the directions say prove thoroughly. Problem number one, cotangent of theta times secant of theta is equal to cosecant of theta. Now, there's a variety of ways I could do this proof. One of them is start with the left and navigate your way to prove the right, or start with the right, navigate your way to prove the left. I don't know if I agree with that one. But anyway, so can we agree that I kind of like left and right meet in the middle? Even though it's not that complicated, that generally is one of my favorite strategies. So I see the left as a little bit complicated. I see the right as a reciprocal trig identity. So that's just the way my brain works. So if you like left to right always, that's totally fine. Me, I like left and right meet in the middle if the left and the right are complicated. So remember that the right is cosecant of theta. And looking at my list of rules, what is cosecant of theta again? That is 1 over sine of theta. And I don't think I can do any more than that. So that's 1 over sine of theta. And hopefully the left side eventually becomes 1 over sine of theta as well. So what do we got here? Well, I can rewrite cotangent, all right, and I can rewrite secant. When in doubt, I like to use the building blocks of trigonometry, sine and cosine. So cotangent is 1 over tangent, but I'm working with secant in the end, so I think I'm going to use cosine over sine for cotangent, and 1 over cosine for secant. So let's do that. Let me get my multicolored pen. So my cotangent, I'm going to make that green. That's going to be cosine of theta over sine of theta. And my secant of theta, I'm going to write that lightly right there. See, it's going to be in red. My secant of theta is 1 over cosine of theta. So now that I've rewritten the cotangent and the secant, you don't have to use color. That's just the way I approach it. So now I can multiply across and get cosine of theta times 1 is cosine of theta. And sine of theta times cosine of theta is just sine of theta, cosine of theta. And now I look at this, can anything cancel out? Yeah. So a cosine of theta cancels out with the cosine of theta on the bottom, and I'm left with 1 on the top over sine of theta. Hey, that's cosecant of theta, or better yet, I like my strategy better, that the left and the right both eventually lead to 1 over sine of theta. So that is a thorough proof that cotangent of an angle times the secant of its angle is equal to the cosecant of its angle. Let's see if we can do number 2, and then we'll expand our toolbox a little bit. So let's look here. We've got sine squared of theta times cotangent of theta is equal to sine of theta cosine of theta. Well, I've got the left and the right. I don't exactly have a super complicated right. I don't see myself rewriting the right side any simpler than that. So why don't I just simplify this part? So sine squared. Well, sine squared is no different than sine of theta times sine of theta times cotangent of theta. The only thing I really did here was write just break down sine squared. That's all I did. Okay, well now sine of theta cannot be broken down even more besides making the sine of theta over 1. And cotangent of theta, if I go back to my list of rules, remember that cotangent of theta is cosine over sine. So I'm going to look at this part over here, and I'm going to rewrite this as cosine of theta over sine of theta. I can see where this is going. This is going to be a huge advantage. So now I'm going to multiply across. So I'm left with sine of theta times sine of theta times cosine of theta. All that over 1 times sine of theta, so sine of theta on the bottom. So now that that's completely simplified, can anything cancel out? A sine of theta on the top cancels out with a sine of theta on the bottom, leaving me with sine of theta cosine of theta over 1, or sine of theta cosine of theta, and that's what I wanted all along. Thorough proof using the list of rules. But now I'm going to expand my toolbox. So the goal for today is, oddly enough, the Pythagorean theorem is going to help us today. So recall that if we have a right triangle and we've got 3 side lengths, leg A, leg B, leg C. Well, recall that the Pythagorean theorem states that the first leg squared plus the second leg getting squared is equal to the hypotenuse squared, or as you might know it, a squared plus b squared is equal to c squared. And you know what? It's so simple, and yet we're going to use it today. Did you guys know that if you take the sine of an angle, you square it, the cosine of an angle, you square it. You add the sine squared plus the cosine squared, you will get 1 every single time. It doesn't matter what angle it is, you will always get 1. So when in doubt, if there's ever an example with a right triangle, I like the basic 3, 4, 5. So I'm going to show this, for example. I'm going to show that sine squared plus cosine squared is equal to 1 using an example, and then I'm going to show a thorough proof. Remember that if we have an angle theta right there for a right triangle, the sine ratio is the opposite over its hypotenuse. So the sine of angle theta in this example is 3/5. And the cosine of this angle is the adjacent over its hypotenuse, or 4/5. So sine squared plus cosine squared, well, I'm not really a fan of this notation, even though all the high schools teach it this way. All the trig textbooks, all the geometry textbooks, all the pre-calc textbooks, all the calc textbooks state that this is sine squared plus cosine squared, or I personally like it as you take the sine of theta and the cosine of theta and you put the parentheses or the brackets around them and square them like that. Well, so now that we know that the sine of theta is 3/5 and the cosine of theta is 4/5, I'm going to plug in sine of theta is 3/5, cosine of theta is 4/5, 4/5, not 4/4, right? 3/5 quantity squared plus 4/5 quantity squared. Well, 3 squared is 9. 5 squared is 25, so 3/5 times 3/5 is 9 25ths. 4/5 quantity squared, that's 4 times 4 over 5 times 5. That's 16 over 25. So therefore, when we add these two fractions, we get the same denominator. 9 25ths plus 16 25ths is 25 25ths. Hey, 25 slices out of 25 total slices of pizza, that's 1. Well, that's just an example. That's not a thorough proof. I mean, who's to say it worked the one time? How does it work for every single time? Well, a thorough proof states, what if we don't put any numbers in there? What if we leave them as leg A, leg B, and hypotenuse C? Let's prove the Pythagorean Theorem of Trigonometry. So suppose that you're given this diagram. You're given that the sine of angle theta is A over C. Suppose that you're given that the cosine of angle theta is B over C. Prove that if the sine of theta is A over C and the cosine of theta is B over C, that any legs A, B, and hypotenuse C will get you sine squared plus cosine squared is equal to 1. So let's start and let's just show it. So sine squared of theta plus cosine squared of theta Well, that's sine squared plus cosine squared. All right. So remember that the sine of theta is a over c, and the cosine of angle theta is b over c. And all I did here was substitute. Sine of theta is a over c, and cosine of theta is b over c. Okay. Well, now I'm going to square each fraction. A over c quantity squared is just a squared over c squared. And b over c quantity squared is b squared over c squared. And all I did here was square each fraction. Okay, so now, because I have the same denominator, I can combine them. A squared plus b squared over c squared, and add fractions. The common denominator is c squared. Okay, add fractions together with a common denominator, I'll say. Well, now I'm going to incorporate the Pythagorean theorem. Hey, remember that in the Pythagorean theorem, a squared plus b squared is equal to c squared. So this part right here, a squared plus b squared, is equal to 1. Sorry, not 1, c. c squared. By the Pythagorean theorem, a squared plus b squared is equal to c squared, and now I have c squared over c squared. Well, anything over itself is 1. So therefore, this is a thorough proof that no matter what in a right triangle, using the previous knowledge of the Pythagorean theorem, we can prove the Pythagorean theorem of trigonometry. And not only that, we've got a new rule. And don't worry, I'm going to send you guys out a Google Doc with all the rules that we're going to use and a little note. Even though it's a bunch of rules, I'm going to say we're going to use the trig ratios and the Pythagorean theorem manipulations. So we're going to prove the Pythagorean theorem manipulations in the next video. This is going to be the next video. What more rules can I conclude from the Pythagorean theorem of trigonometry? See you then.